If you've ever looked at a satellite image of the Earth, there's this undeniable, almost hypnotic beauty to it, especially when you're looking at a major weather event from
Oh,
space.
totally. It just looks pristine, right? Like
Yeah.
this perfect fractal swirl of white clouds rotating silently against the deep blue of the ocean.
Yeah, exactly. It looks like a painting.
But it has this geometric perfection that completely masks the reality of what you're actually looking at.
Right.
Because, from orbit, a cyclone is just a marvel of atmospheric physics. It's a beautifully balanced equation of thermodynamics and fluid dynamics.
Right. Playing out in a vacuum of silence.
Exactly.
But then you zoom in, you drop down through those pristine white clouds, hit the ground, and suddenly that beautifully balanced equation is it's a violent, chaotic monster tearing apart entire communities.
Yeah, the contrast is really stark.
And that tension, right, that tension between the scientific awe and the sheer human devastation is what we are exploring today in this deep dive. We are going to look at the 2020 typhoon BAVI. This was a storm that had meteorologists absolutely glued to their monitors, watching it grow into this, textbook scientific marvel.
Yeah, they were amazed by it.
But as we'll see, it ultimately unfolded as a devastating humanitarian disaster across the Korean peninsula.
We have a really comprehensive stack of sources to guide us through this today. We're pulling from satellite meteorological data, advanced climate attribution studies, and some highly detailed disaster impact reports.
And those detail the fallout in both South and North Korea.
Right, exactly, both countries.
And, before we get into it, just a quick note on how we handle this kind of data. Because this deep dive will cover impacts across both South and North Korea,
Right.
we are simply here to impartially report the facts and the meteorological data straight from the original source material.
Right, we're just looking at the data.
Exactly. We aren't endorsing any political viewpoints. Our only goal is to convey the physical realities on the ground exactly as they were recorded in the sources.
Just the science and the impact.
Okay, let's unpack this. Because before we look at the sheer destruction on the ground, we actually need to go back up into space.
Right.
Because the way the sources describe the storm's formation, it sounds less like weather and more like a Hollywood special effect.
It really does. The imagery we have comes from the Himawari 8 satellite.
Okay. And what exactly is that?
So it's a geostationary weather satellite.
Yeah.
And it can take high-resolution infrared images every 10 minutes. The reports actually call the footage it captured of Typhoon BAVI a God's eye view.
Wow. God's eye view. That's intense.
Yeah, because when you watch the animation of BAVI's development over the ocean, you are watching a highly organized textbook storm rapidly grow and structure itself in real time. It's a literal masterclass in cyclone genesis.
And the name itself feels incredibly fitting for what that satellite was seeing. The name BAVI was contributed to the International Registry by Vietnam, and it translates to mountain range.
Which is not an exaggeration at all when you look at the physical dimensions of this thing.
Not at all.
The meteorological community in the sources refer to BAVI as a super fat monster.
A super fat monster. I love how technical that sounds.
Right. But to understand why, we have to look at its wind radii. The data shows it had a level 7 windstorm radius of 380 kilometers.
Okay, hold on. Let's ground those numbers for you listening, because level 7 doesn't mean much without the physical context, right?
Yeah, fair point.
On the regional wind scales used in these reports, a level 7 wind is near gale force. So that's roughly 30 to 38 miles per hour. That's enough wind to put whole trees in motion and make walking against the wind incredibly difficult.
Right.
And BAVI maintained that wind speed across a 380-kilometer radius. That's a 760-kilometer total diameter.
To visualize that footprint, if the eye of the storm were, say, over New York City,
Okay.
those gale force winds would be simultaneously battering Washington, D.C. to the south and Boston to the north.
That is massive.
And the level 10 inner radius, which signifies storm force winds of about 55 to 63 miles per hour.
Which is capable of uprooting trees and causing severe structural damage, right?
Exactly. That radius extended 180 kilometers out from the center.
The sources note that a storm of this sheer physical width makes the entire island of Taiwan look small by comparison.
Oh, easily.
Depending on the specific historical metrics you look at in the reports, BAVI was the largest storm of its kind in anywhere from 25 to 63 years. But wait, I have to push back on this logic for a second.
Okay, go ahead.
If you take a set amount of thermodynamic energy and you stretch it over a massive 380-kilometer radius, shouldn't the storm inherently be weaker?
How so?
Like spreading a tablespoon of butter over a massive piece of bread. Why isn't a tight, compact, small steel cannon type of storm, much more dangerous to us on the ground.
Well, the butter on bread analogy makes sense intuitively, sure, but weather operates on the physics of kinetic energy.
Okay.
The total kinetic energy of a cyclone doesn't just scale linearly with its wind speed, it scales with the square of its radius.
Ah, the square of its radius.
Yeah, right. So the total volume of moving air in a 380-kilometer wide storm is exponentially larger than a compact storm. A compact storm might have higher absolute peak winds right at the eye wall.
But it moves past you relatively quickly, right?
Yes.
Ah, so it's a matter of duration.
Duration and displacement. A super fat monster like BAVI subjects a single location on the ground to battering winds and torrential rains for many, many hours. It is relentless, compounding structural stress.
That sounds exhausting.
It is. Furthermore, a wider storm acts like a massive atmospheric bulldozer. It pushes a vastly wider footprint of ocean water ahead of it.
Storm surge.
Exactly, the storm surge. The sheer volume of ocean water physically lifted and pushed onto land impacts a much larger stretch of coastline. So while the wind energy might be spread over a larger area, the sheer amount of water being moved is catastrophic.
Okay, and here's where it gets really interesting. Because a storm moving that much air and that much water takes an unbelievable amount of continuous energy to keep spinning.
Oh, absolutely.
But BAVI didn't just maintain a steady spin, it pulsed. The data shows it had 3 highly unusual, distinct peaks in intensity, eventually reaching maximum wind speeds of 60 meters per second.
Which is incredibly fast.
Right. So how does a storm that massive sustain itself over such a long journey without just, starving itself of energy and collapsing under its own weight?
Well, it comes down to a mechanical process called an eye wall replacement cycle.
Okay, break that down for me.
So BAVI was pulling in so much heat and moisture from the ocean so rapidly that it essentially outgrew its own internal structure.
Yeah.
In a highly intense cyclone, this central eye is surrounded by a towering ring of thunderstorms. That's the inner eye wall.
Right, the really intense part you see on the radar.
Exactly. But as BAVI expanded, the outer rain bands began to rotate faster and consolidate into their own solid ring, miles outside the center.
So you end up with 2 concentric rings of thunderstorms, a double eye wall.
Yes. And that outer ring essentially forms a blockade. It intercepts all the warm, moist inflow of air that the inner eye wall needs to survive.
Wow, so the inner eye wall is basically starved of its fuel.
Exactly. Furthermore, the air between the two walls begins to sink, which actively suppresses the inner storms. The inner wall collapses, the eye fills with clouds, and the massive outer wall gradually contracts inward to take its place.
That is wild.
The sources actually compared this specific behavior to the infamous typhoon Sudlor from 2015, which went through a very similar, highly destructive reorganization.
So wait, does this double eye wall phase basically act like a pit stop in a race?
A pit stop.
Yeah, like the storm is pausing to upgrade its engine before speeding up to its next peak?
That's actually a great way to put it. The mechanics are very much like a pit stop. The storm's overall intensity might plateau or even temporarily dip as that old inner wall collapses and the new, wider outer wall contracts and takes over.
Right.
But once that massive new upgraded engine is locked into place, the storm accelerates again, drawing in even more energy and reaching a new peak. And BAVI executed this complex mechanical maneuver multiple times.
But a pit stop requires a fresh tank of fuel, Where is this storm finding the energy to rebuild its engine 3 separate times?
It found it in an exceptionally long, artificially hot runway of ocean water.
A runway?
Yeah. First, we had El Niño conditions, which naturally pushed a massive pool of warm water into the central and eastern Pacific.
Okay, so that gave BAVI a massive geographical stretch to travel over.
Right. But the critical variable was climate change.
Ah, the attribution studies.
Yes. What's fascinating here is how the invisible driver of climate-fueled ocean heat directly manifested into the visible mechanical restructuring of that double eye wall.
It's just crazy to think about.
The attribution studies in our sources found that BAVI was intensifying over marine heat waves, stretches of ocean that were abnormally dangerously hot.
And the reports state those specific marine heat waves were made up to 80 times more likely by human-caused climate change.
80 times.
But how do researchers even calculate a number like 80 times more likely? Like, how do you prove that heat wave wouldn't have just happened anyway?
They use immense computational climate models. Researchers basically simulate the Earth's climate thousands of times over.
Like running a video game simulation.
Exactly like that. They create one virtual world that includes all of our historical greenhouse gas emissions, and another virtual world that entirely removes human emissions. simulating a pre-industrial climate.
Oh, that's clever.
Then they run the tape forward in both worlds and count how many times a specific extreme marine heat wave occurs. In the pre-industrial world, a heat wave of the magnitude BAVI encountered is virtually non-existent.
Wow.
But in the world with our current emissions, it pops up constantly.
And so the math spits out an 80-to-1 ratio.
Exactly. That excess thermal energy trapped in the ocean is the direct fuel source. It's what allowed BAVI to pause, rebuild its engine, and re-intensify to pack winds as high as 290 kilometers per hour.
That's roughly 130 miles per hour.
It was a climate-fueled machine.
Well, all of that kinetic energy gathered over the ocean has to go somewhere, right? The runway eventually runs out. So let's bring you down to Earth to examine what happened when this 380-kilometer-wide, upgraded engine of a storm slammed into the Korean peninsula.
Yeah, when a system with that much power meets human infrastructure, the physics are incredibly unforgiving.
To put it mildly.
The immediate impact upon landfall in South Korea was a massive failure of critical systems. The reports detail 1,633 widespread power outages.
Geez, 1,633.
The sheer wind load compromised the structural integrity of the grid. The storm damaged 401 public facilities, tearing apart roads, bridges, and ports, and severely hit 149 private facilities.
And the wind is really only half the equation here. The massive dome of ocean water BAVI pushed inland rewrote the record books.
Oh, absolutely.
The flooded data from Incheon's Gangwon Bridge is particularly jarring. The water level at that bridge reached 7.7 meters.
For context, 7.7 meters is over 25 feet of water.
That's insane.
It's higher than a two-story building. And it's crucial to remember that water is incredibly heavy. A single cubic meter of water weighs a metric ton.
So when you have a 7.7-meter wall of water moving inland,
it acts like a liquid battering ram against anything engineered to withstand normal tidal flows.
It actually obliterated the previous historical record for that specific location, which was set in 2010 at 5.46 meters.
Right.
So BAVI beat the all-time historical record by over 2 full meters. That is not just a bad weather day. That is a fundamental paradigm shift in what the infrastructure was built to handle.
Exactly.
I mean, a seawall built for a 5.5-meter flood is entirely useless against a 7.7-meter flood.
And we connect this to the bigger picture.
Yeah.
BAVI's true danger in South Korea was that it wasn't an isolated event. It was the vanguard.
Oh, right. There was more coming.
BAVI was immediately followed by 2 more typhoons, Maysak and Haishin.
Back-to-back-to-back storms. That's just relentless.
It is. BAVI did the initial breaching. It battered the seawalls, eroded the levees, saturated the ground, and compromised the public facilities. It effectively stripped away the region's armor.
The ground was so saturated from BAVI that it could not absorb another drop of moisture.
Precisely. So when Typhoon Maysak arrived shortly after, the region was utterly defenseless.
And Maysak didn't hold back, did it?
Not at all. Maysak dropped a staggering 1,004 millimeters of rain at Jeju's Melthala.
1,004 millimeters.
Yeah.
That is over a meter of rain.
It broke an 18-year local record. The floodwaters from Maysak and then Haitian right behind it were pouring into river systems and coastal areas that had just had their flood defenses completely compromised by BAVI.
I mean, just try to imagine that for a second. Imagine boarding up your house, surviving a record-breaking 7.7-meter flood that totals your neighborhood.
Yeah.
And as you step outside to assess the damage to your town's levees, you realize you've just survived round 1 of a 3-round heavyweight fight against nature.
Terrifying.
And rounds 2 and 3 are already on the radar. The compounding effect makes disaster resilience almost impossible. It's like psychological torture on top of the physical destruction.
It really highlights a critical vulnerability in disaster planning. Most infrastructure is designed to survive a single, massive design basis event.
Right, a one-off.
It is rarely engineered to survive 3 extreme events back-to-back in a world where these storms are retaining more energy and occurring with greater frequency.
That's a scary thought. But the storm didn't just stop at the border, though. It kept grinding north. And as we move geographically into North Korea, the focus of the disaster entirely shifts.
It really does.
It goes from a crisis of damaged bridges and power grids in the south to a silent existential crisis of human survival.
The manifestation of the disaster in North Korea was fundamentally different because of the specific geography of the storm targeted. On August 27th, Typhoon BAVI made landfall in North Korea's South Hwanghae province.
Okay.
It hit with maximum sustained winds of 37 meters per second, which registers as a Beaufort scale 12 so, hurricane force.
But in South Hwanghae, it wasn't the cities that took the most critical hit. It was the dirt.
Right. South Hwanghae Province is the agricultural heartland of North Korea. It is the country's largest producer of both corn and rice.
It is literally the breadbasket of the nation.
Exactly. When a storm of this magnitude hits a vulnerable agricultural center, it doesn't just destroy buildings, it destroys the future food supply for millions of people.
And the timing couldn't have been worse. The typhoon made landfall right at the end of August. In that specific region, the corn harvest begins at the very end of August, and the rice harvest follows in late September.
The worst possible time.
Right, because this means the crops were completely mature, the stalks were heavy with grain, making them highly top-heavy and incredibly vulnerable to being snapped by the wind.
They're also highly vulnerable to submersion. When mature rice and corn are submerged in floodwaters, the soil becomes anaerobic. It's starved of oxygen.
Oh, wow.
Yeah, the root systems begin to rot almost immediately, and bacterial infections spread rapidly through the weakened stalks.
It's like a cruel joke. You nurture a fragile crop all year, fighting pests and weather, and just days, literally days before you can reap the reward and secure your family's food for the winter, a meteorological mountain range drops out of the sky and crushes it.
Just like in South Korea, BAVI in North Korea was the climax of a compounding disaster. We have incredible data here from the GeoGlam report.
GeoGlam. What exactly is GeoGlam, and how do they know the soil conditions before the storm even hits?
GeoGlam stands for the Global Agricultural Monitoring Initiative. They use an array of Earth observation satellites equipped with microwave sensors.
Oh, fascinating.
These sensors can essentially peer into the top layer of the Earth's crust and measure the dielectric properties of the soil, which tells researchers exactly how much moisture is locked in the ground on a global scale.
That's amazing tech.
It is. And they had been closely tracking the soil conditions in South Hwanghae prior to BAVI's arrival.
And what did those microwave sensors show?
The region had just suffered through an agonizing 2-week monsoon season. The soil was completely saturated. South Hwanghae had just recorded its highest seasonal rainfall since 1981.
Since 1981.
Wow. The ground literally could not absorb any more water. So when BAVI's massive rain bands arrived, the water had nowhere to drain.
The bucket was already full.
Exactly. The extreme winds and rain destroyed the agricultural levees and completely submerged the crop fields. The GeoGlam report plainly states this single event plunged the area into severe food supply difficulties.
So what does this all mean? It turns a meteorological event into an immediate, silent humanitarian crisis. I mean, a bridge in a city can be rebuilt relatively quickly with heavy machinery, steel, and concrete.
True.
But a destroyed harvest cannot be rushed. You can't speed run the growth of a new crop. You just have to endure the hunger until the next season.
It is a stark biological limit, and it perfectly encapsulates the duality of Typhoon BAVI.
It really does. Let's take a step back and recap the journey we've taken through these sources today. We start up in orbit, watching BAVI as this beautiful, terrifying, textbook example of atmospheric physics.
Right, the God's eye view.
We saw a super fat monster with a 380-kilometer radius fueled by ocean heat waves that computational models tell us were made 80 times more likely by human-caused climate change. We watched it pause, rebuild its engine with a double eye wall, and peak 3 distinct times.
And then we followed that kinetic energy to the ground. We saw it rewrite the engineering history books in South Korea, shattering a decade-old flood record with a 7.7-meter wall of water.
Just incredible numbers.
And systematically stripping the region's physical defenses just in time for 2 subsequent typhoons to drop a meter of rain on Jeju Island.
And finally, we tracked it north, where it struck the agricultural heartland at the worst possible moment in the harvest cycle, turning a battered infrastructure system into a quiet, devastating crisis of food security.
It's a lot to take in.
It is, and this is exactly why understanding the mechanics of these storms matters for you. It's so easy to look at climate change as an abstract concept, lines on a graph showing ocean temperature anomalies.
Right.
But the story of BAVI shows how macro-level global climate shifts translate directly and violently into micro-level human suffering. An anomaly in ocean temperature directly results in a family lacking the food they spent a year growing.
This raises an important question, though. As we look at all this data, the God's eye view from the satellite, the physics of the eye wall replacements, and the broken levees on the ground, we have to look toward the future.
Okay, what do you mean?
Well, if a storm with a 380-kilometer radius that stops to rebuild its own internal structure and hits 3 separate intensity peaks is considered an extreme textbook marvel today,
Yeah.
As our oceans continue to trap unprecedented amounts of thermal energy, how long will it be before a super fat monster like BAVI isn't the exception, but simply the new normal for our textbooks?
Wow. When that pristine, perfect swirl of white clouds we see on the satellite isn't a rare cinematic event anymore, but just another Tuesday on a warming planet.
Exactly.
It makes you look at those beautiful satellite images completely differently, doesn't it? Keep asking questions, and we'll catch you next time on The Deep Dive.